Thank you very much, Des. It's fantastic to speak to you all in this beautiful, beautiful venue. So I teach at the Bartlett at UCL. I'm also doing research, doctoral research into the latent space, and I've been looking really at what different kinds of models are being used both across education and in academia. And perhaps the luxury or responsibility that occurs, I think, in education, and a lot of the educational research and practice, is to really ask this question: what role AI models may have in the architectural process. And there's this opportunity to really test different kinds of data, different kinds of models, where they sit in the process overall, and really analyze where the agency sits, where the responsibility sits, and many of the questions that have already been raised. So I won't go into the detail of this, but I've been looking at the different kinds of AI teaching across architecture schools, both in the UK and across the world, and looking at the different balance of kind of where opportunity occurs in terms of teaching around image ideation or more detailed aspects of the process, and then similarly looking at the academic research that's emerging from around the world at the different stages of design. And perhaps it's not a surprise from some of you who've seen it that the biggest impact in the last few years has been around a lot of the image generation or the ideation or the idea of kind of being able to mine the internet to generate new kinds of ideas or generate 3D forms or videos from sets of text prompts. But there are other opportunities as well that track through the design process, and some of these are particularly important perhaps in terms of how we address sustainability. And so in my kind of analysis, I've kind of been looking at how these kind of categorize, both in terms of design development, some ideas about optimization, but also multimodality, which I'll come on to, and then other aspects where it's really more about the ingredients. And I think what's important is to understand what deep learning, the particular model of AI that has emerged in recent years, what it's good at, what it's bad at, and how its understanding of kind of intelligence might reflect in terms of our understanding of what architectural intelligence is. So I think the important thing to understand is there's quite a paradigm shift in maybe what we're used to computing doing and what computation is good at, from broadly a sense of rules and systems to actually being driven by examples. So this approach to deep learning, where we take a set of examples, we take data, and then we infer actually what that pattern shows, is now this dominant method in the way in which AI is working. So the neural network you see here, which is learning patterns and connections through training by being exposed to examples of data, whether it's lots of handwriting or so on, it infers this pattern. And this is hidden largely in a black box. It's too complicated to understand, but what we're doing is we're deriving some kind of understanding of rules purely from the data that we're given. And this is a very different kind of understanding of intelligence than setting down and establishing a series of rules from the outset. And when we go back to 1986, this period when deep learning was really born, with people like Jeff Hinton, which you may have heard of before, who recently got the Nobel Prize, they state actually very explicitly even then that the role, as it says here, we do not assume the goal of learning is the formulation of explicit rules. Rather, we assume it is the acquisition of connection strengths which allow a network of simple units, which is your neural network, to act as though it knew the rules. And this is a really important emphasis. When we train these networks, they are performing as if they understand the rules, but those rules are not ever actually kind of encoded in any intelligible way. So our only way to actually teach a pattern or teach a certain behavior is through examples. So we've moved from this understanding where we can set down a set of principles that are intelligible, that we all agree with, which might have kind of ethical or agency and considerations within a professional framework. We're not doing that with necessarily deep learning. What instead we're doing is we're working only with the examples of the outcomes we want. And then what the black box does, what neural networks do, is they take those examples and then they can either make more examples, or they can change that data, or they can reflect the pattern that those examples reflect. But we don't get to set those rules themselves. They are just discovered through the neural network training. And I think this is quite interesting when you consider some of the dilemmas that sustainability has, because if we say take the recent UK net zero standard, the pilot, when setting the limits, there's been these two approaches. There's been a top-down approach of let's set budgets for every industry and every kind of subset of the economy as to what kind of carbon they should use. But then we also work from case studies and we work from examples, because there's a specificity. In the end, we just need to know what's possible in real life. So we've always got this tension, even when we're thinking about sustainability, between a kind of a model, an idealized idea of how we would spend carbon, what are the principles, what are the parameters, and then this tension which is about actually what is possible, what do we actually achieve in real life, what can we measure in examples. And we're actually moving to the right-hand side. We're now much more dependent on examples and data to infer these rules. So if we consider architecture as a total process, this sort of graphic attempts to really describe how we have this same tension in the architectural process. We work with ideas of brief and context, or style, or regulations. We have a set number of suppliers. We have standards. These are all parameters which are broad, they're abstract, and they kind of define the way we might want to do architecture and the kind of scope we have and the domain we have to work. And then gradually, as we insert more context, as we insert the specificity of every project, this becomes sets of drawings, this becomes specifications, this becomes tenders, and then it eventually filters down to individual buildings, all with their individual performance. So the challenge we have is we've moved from a system where sustainability might just be governed by best principles and a kind of idealized idea of how we might expend budgets of carbon, parameters by which we might try and act with responsibility to the environment. And actually we're now looking at, well, can we learn from best practice? The challenge, of course, is we're in a time when we want to make lots of low carbon or zero carbon buildings, and we don't have those out there. We don't actually have this big database of, even if we could get all the complexity of the data, we can't necessarily infer from those final buildings to say what is the pattern, what is the solution. So architecture as a total practice is somewhat resistant to a kind of grand training that will simply say, here are all the things we want to create, now let's learn how to make them through deep learning. But we have to therefore sort of break that down. And in sort of reflection of what I've also found in terms of where machine learning is appearing, it's actually, there's a symmetry to this process as well, because many of the parameters and rules and brief and regulations and models that we might use, well, they're all inferred from real life. They're inferred from going out there and trying to work out what is the best set of ideas that we should have, or what is the correct brief for this building. Normally they might be set in abstract, but of course now with machine learning we might be able to infer those. So we might actually be able to consider what are the ingredients that go into architecture, and can we actually, through data, through sampling, actually use some of AI to make better systems or make more accurate data that we then feed into the architectural process. So I think there's really these two patterns. There's the process itself and then actually what we're working with. So in terms of better ingredients, I'll try and sort of highlight some different approaches in terms of models, what's appeared, how people are working, and then go on to the other half. So one of the key questions with, say, better ingredients is the simple idea of what is the architectural brief that we're working with. And a very pertinent question at the moment is retrofit versus new build. This is a highly entangled, difficult, complex problem. It's not as simple as you see here with kind of text and image generation. But perhaps what we need to do is think about how can we start to model and understand some of those questions to answer in every site, what is the right answer. At the moment, we're sort of, there's a suspicion that these rules and systems are kind of open for exploitation by individual clients who might want to have one solution or another in terms of how they calculate things. And then there's lots of opportunities to do this. So we have ideas of machine vision, which we can apply to the city. We can start to look at different ways of classifying, understanding, and processing what these buildings are, seeing them in different ways, and reading the encoding in different ways. There's projects which have looked at how you might identify which buildings are best for retrofit just from images, because you can then sort of highlight down where this complex problem could be addressed. This is a project in Cambridge. We also have a broad range of urban data that we can look at for different kind of latent patterns. So there's an enormous opportunity now to find and mine the data within cities to identify different communities, different interests that might actually change what the brief for a building is. So it can be more sustainable, it can engage with different communities, it might actually work better, the brief might work better. And getting a better brief and getting a better match to what it needs to do is half the sustainable problem, of course, because in the end we're interested in the longevity of these buildings and the flexibility of these buildings. Another aspect of the sense of better ingredients actually comes in terms of the actual materials. So this is computer vision applied to concrete aggregate. But the advantage with being able to actually be more specific about some of these materials is then you might actually be able to infer more things about their physical properties, their engineering properties. You might actually be able to engineer these better because you're not working with such crude parameters. You might have a much more precision into the ingredients and components that you put into architecture. And there's a kind of broader narrative and ambition about this in terms of what's called Industry 4, where you start to link up all these ideas in an ecosystem where you might have different additive manufacturing or advanced manufacturing methods. You might be scanning materials, you can combine computer vision, and you can be using this to basically make a pipeline that says, I've got a much more precise idea of how this material is going to behave, which ultimately, could result in less carbon. And to take this is a student project, but kind of to take a similar idea about how you are more accurate about the ingredients. This was interested in the natural variation that you might get in the Bobley Gardens in Venice of this kind of rusticated stone. This is normally done as a sort of, a romantic idea, but the student looked at this in terms of, well, how do I train a data set with precise probabilities? So actually, natural variation in stone is something that I can simulate much more accurately through a deep learning model. So what they were then able to do was train a model that understood the variation of these stones with precise probabilities through a 3D GAN. And this then builds up this collection of stones, this collection of ingredients, which can then be much more precisely understood in terms of how likely they are to occur on the site and how they might then be combined and how they might be all connected together. So having done this training method, what that then means is you have an architecture which has, in some sense, naturalistic variation, but actually there's an underlying machine learning model which really understands the precise variation of these pieces. So in one sense, they speak to a certain language which we might find comfortable in architecture, which doesn't look standardized, but actually there's an underlying probabilistic model. And then the other side of this is standardization. So some of what we might find as an opportunity with low carbon would be to actually make the connection from design through to construction more efficient, to look at how we might standardize components, but then use AI to allow a degree of variation and customization between that. So we see projects from Zurich and also the AUAR, which is a kind of building little micro factories for building housing. So connecting these up can work really well. And it works best when you make the problem simple. So that's why it tends to work with certain defined architectural typologies where perhaps we're very clear about the input of the design parameters through to the final construction output. In an even more defined domain like computer code, this has already been shown to work really well. So DeepMind did a project called AlphaDev, which followed on from AlphaGo, where within the limits of simple sorting algorithms, they found a method of rewriting the sorting algorithm so it was 70% more efficient. So this is a very kind of obscure detail really, but it's an algorithm that's used in masses of computing around the world. And by simply reprogramming it in a way that a human wouldn't have found, they managed to find a 70% saving on its energy efficiency, which then has a massive impact for computation and energy consumption around the world. And that's because it's a neat problem that can be recalculated, in effect. It can be so the architectural analogy might also be when you have a particular typology that can be heavily standardized and you can connect design all the way through to construction. When we look at process, so that's dealing with the ingredients, what we're dealing with then is how do we actually capture all the design iterations and this flow of information, which might be a set of simple parameters to begin with, but then move through drawings and models and become highly specific down to individual buildings. So how do we make these sustainable and capture this sort of changing level of certainty as we approach construction? Certain areas, there's kind of clear opportunities. So DeepMind, again, they released a model fairly recently that proved that they could do the weather forecast with less computation arguably as reliable, they said, as the huge simulations run by the Met Office. And this was just basically working on, next day data. So you take a load of data and then you can predict it fairly reliably on the next day without necessarily simulating it all with the huge computational fluid models that the Met Office might use. And this is similar to some of the kind of heuristic techniques that are then used with Forma, which I think we'll hear from shortly, the Autodesk product, which again is dealing with simulations in a way which is basically gives you a much faster response and is very useful in a design context because you can effectively get a surrogate model which will give you fairly instant feedback on design changes you make. And what they effectively do is they're sort of entangling representation with prediction. So the one on the left, this is a different project, but is about taking just simple plans and then predicting how the daylight behaves. It's not simulating it in the conventional sense. It's not intelligible. It's not something that we can rerun. But what it does do is it matches patterns of information. Because you get that immediate feedback, that means that optimization processes can potentially run much faster. So you can also shift things around in the project on the right, which deals with then adjusting the parameters of the building and getting immediate feedback to optimize. But what I think is quite interesting about this is there's also the opportunity to reverse it, which is not really how simulations work. Because this is more about mapping one kind of information to another. This project takes, in effect, the blocks you see here, this simulates a series of performance attributes, so the impact on these buildings, with the buildings in the foreground. And then actually the model can then infer different arrangements of those buildings which have the same performance impact on those buildings. So having established a certain performance, it will then change around the design parameters to match. So it's a kind of reverse simulation. And that's because we're not really simulating it anymore. We're dealing with the correlation between different patterns of information, different drawn information. And for me, this is a really important difference because in terms of process, we're moving really from the idea of simulation to what I would call multimodality. So you might be familiar with multimodality in terms of text to image or kind of quite obviously different modes, but actually machine learning, it doesn't really matter. It can learn from any kind of pattern of information to another pattern of information. And for me, I think this is what's really interesting for architecture and offers a real opportunity, because when we're talking about retaining degrees of agency and in integrating models into this design iteration process, this is something that architects do naturally anyway when we're managing uncertainty and we're trying to make the right decisions as we move from broad parameters through to individual buildings. Architecture has always used models and drawings as a method of effectively managing the design process, managing where the parameters are, but then also being specific and then critically reflecting on that. And this is really essential in the way in which, when we're dealing with carbon, we have to deal with this increasing granularity and this increasing shift in information. As we move through the design process, we have lots of inputs, lots of technical inputs, and we use the design process to effectively manage this uncertainty. And I think it's the transmission of information through different modalities. If you consider every drawing that an architect produces is a different modality, which works at a different scale, it works with different information, it works with different degrees of certainty and uncertainty. And it's actually the conversations around this and the interactions around this is actually naturally how we manage the process, the assumptions of carbon from one step to another. Machine learning is very good at this. So the style transfer methods you see, it can actually learn the pattern, say here, from a drawing. So you might input a drawing and it infers then a model. It's very reliable at this and it can work actually with much smaller data sets. And what's most important, of course, is that we're inputting one thing and then getting out another. So there's more accountability and more control over these processes. This is another student project, but this shows how you can train with quite simple models drawing transformations. You can have an input and an output. So you can train a model to learn from a footprint to the outline of a building, the outlines of a building to the zones, and you can build up this as a chain of models which then actually infers a whole 3D building. This is partly contextual based on the buildings that you've trained it on, so this was based on churches in Venice. And it's a quite creative, speculative tool. But the important thing is you're dealing with an augmentation of the design process where you get to insert a certain amount of intelligence in this chain of drawings without necessarily losing all the intelligibility and agency. Similarly, this was a project which dealt with the multimodality between drawings and music. It's a much more speculative, creative project, but effectively by mapping in one space music composition and drawings, which is entirely constructed process, there is this opportunity then to move from the sonograms that you see on the left to the models on the right. And actually you can then design a building where you've got two goals. You're actually composing a piece of music and you're composing a piece of architecture. This is a very creative, speculative thing, but the point being that this could also be about composing a piece of architecture and meeting a sustainability objective, being considerate about the amount of carbon. We can start to manage those two goals if we have drawings to deal with them and we have data to deal with them and we cross-train them. This idea of managing architecture through different kinds of syntax, we already see explored in different ways. So where we start to get models interacting with language, or we start to describe form and models through different forms of language here in terms of symbolic trees or descriptions of functions. And lastly, there's obviously a grand aim of analysing the amount of carbon and improving the performance targets and there's many calculators out there which might be tracking how we actually do this, and there's a general desire to improve the prediction of this. But I think perhaps what's as important or more important is actually how we deal with these numbers through the design process. The ability to predict the carbon and accurately control it is infected by the power we have and the agents we have at every stage of the design process, our ability to change this. So really, for me, the advantage with trying to think about carbon in a multimodal way, to think about what kinds of drawings, what kind of methods we might use through the design process to track carbon and how that might feed back to us, is it actually is more empowering about the decisions we make. It's not then a question of just saying, we start from almost nothing and then it outputs a fully low-carbon building. I don't think that's realistic within the complexity of architecture. And if there's a sort of precedent which we can look at already, which suggests how that could develop an architecture, how that could be really useful, then actually I'd just say ChatGPT is one of the most interesting examples, because, as you may be aware, when you ask it to give it a prompt and it gives you an answer, which all of you maybe now be familiar, the color coding in the bottom left shows the natural state which the transformer would see. It doesn't reveal this to users, but it's picking every word with a probability. So the green ones are more probable, the orange ones less so, the red ones it was really not sure about, but it still gave it as the next word. And this is what transformers are very good at. They're very, very good at calibrating uncertainty in its answer. And so then I would really leave it, as I think that's probably the greatest opportunity for carbon, is to think about more these kinds of models that can track our design changes. They can track the evolution of drawing to drawing, model to model, and as you see here, sort of actually guide us as a sort of helpful agent alongside our design process, because they know you're drifting towards a good building or bad building in terms of carbon. I think that would most ideally reflect the way we naturally work and actually retain some of the agency and intelligibility within the process. I notice there are some simple examples, so my last slide, but this is the Google DeepMind project, which is about learning to paint. And in effect, this is not trained in a normal sense of just on the output. It actually learns as an agent the sequence of steps and paintbrush techniques that can actually reconstruct these faces, and it can reconstruct them with different levels of abstraction. And I think this is a good analogy, really, because if we can teach it to paint faces, then we should, with the same synthetic data that architects might go and create, we can actually teach an agent to design good buildings. That doesn't necessarily mean we're going to be able to hand over all control, but they can necessarily sit with us in a design process and give us some guidance, green or red, as to whether we're drifting towards a better solution or worse solution in terms of carbon. So that's all for me, and I look forward to your questions later.